Welcome to Hypnos Helix. I'm so glad you're here. Before we start, I'm curious to know where in the world you're watching from this evening. From a quiet home, a cozy cafe, or a terrace with the sound of rain. Wherever you are, I hope you're warm and at peace. If you enjoy these tranquil reflections, a subscription and a like would greatly help this small channel continue its journey. And to all who have already subscribed, thank you. Your support means a great deal to me. Today's topic shouldn't be too exciting, but if it does make you think, at least you'll understand why light can be both a wave and a particle, and why the world around us isn't as simple as it seems. It's a small price to pay for a sleepless night. So let's begin. What is quantum physics? And why does it often sound like the universe is making up the rules as it goes? The world we see and touch seems stable and predictable. If you let go of a cup, it falls. If you flip a coin, it lands. If you close your eyes, the moon doesn't disappear. But in the early 20th century, scientists started looking closer, much closer. And the deeper they delved into the nature of matter, the stranger things got. Light, they discovered, could behave as both a wave and a particle. Particles could be in many places at once until they were measured, and the act of observation didn't just reveal what was already there. It seemed to change it. This wasn't a quirk of bad data or blurry equipment. It was real, reproducible, and it shattered the orderly laws of classical physics that had stood for centuries. Quantum physics wasn't just a new branch of science. It was a new way of perceiving reality, strange and shimmering, where certainty is replaced by probability, and where a cause doesn't always precede an effect in the way we expect it to. In this video, we'll gently dive into this world. There's no need to understand every equation or memorize every name. We'll move slowly from one mystery to the next, from the earliest puzzles that force scientists away from classical notions to the modern questions that still keep physicists awake at night. So get comfortable, close your eyes if you wish, and let's begin exploring a world where even emptiness isn't truly empty, and where everything you thought was real is most likely just one of many possible states: blackbody radiation and energy. Quanta at the turn of the 20th century, physics seemed almost complete. The laws of motion were understood, thermodynamics was orderly, and light was neatly framed within electromagnetic theory. It was a golden age of certainty. Some scientists even believed that all the major questions had already been answered. There were just a few oddities left to clear up, like dust in the corners of a well-swept room. One of these dusty corners concerned a very simple idea: what happens when you heat an object? When you heat a piece of metal or coal, it begins to glow, first red, then orange, then white, depending on the temperature. This glow, called blackbody radiation, happens because of how objects emit electromagnetic radiation when heated. It was easy to observe, and it seemed like it should be easy to explain, yet the math refused to cooperate. Classical physics, using the known equations of the time, predicted something bizarre. According to the formulas, as a blackbody's temperature increased, it should radiate more and more energy at shorter and shorter wavelengths, especially in the ultraviolet range. The problem? This prediction led to infinite energy at high frequencies, a scenario so impossible and ridiculous that it was nicknamed the ultraviolet catastrophe. No amount of fiddling with classical equations could stop the math from spiraling into nonsense. Reality simply didn't match the predictions. Some enter Max Planck. In 1899, Planck was a German theoretical physicist with a reputation as a careful scholar. He wasn't particularly radical or a rebel. In fact, he was a staunch believer in the classical worldview, but he was also pragmatic. And faced with the blackbody radiation problem, he did something quiet but revolutionary. To fix the math, Planck introduced a small, strange idea. What if energy couldn't be emitted in just any amount? What if instead it came in tiny, indivisible packets, like coins you can't split in half? These packets would represent the smallest possible units of energy. He called these packets quanta. This was a sharp departure from the continuous view of energy accepted in classical physics. Instead of a smooth flow, energy had to come in steps, tiny jumps that depended on the frequency of the radiation. Planck even introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was unimaginably small, yet mathematically elegant. When he plugged this idea into his equations, something amazing happened. The problem of infinite energy vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet catastrophe, yet he didn't quite believe it himself. In fact, Planck himself described his solution as a mathematical trick, a clever way to make the numbers behave, but not as a description of how the universe was actually put together. He assumed that future physicists would find a better explanation. That didn't require such bizarre assumptions. Quantization was a temporary fix for him, not a fundamental truth. What he couldn't have known at the time was that his trick would become the cornerstone of a whole new way of thinking. His idea that energy comes in discrete packets laid the foundation for quantum theory, a theory that would soon shatter much of what classical physics took for granted. It's easy to look back and see this as the moment everything changed, but at the time, it felt more like a strange footnote than a revolution. Planck didn't set out to challenge the foundations of physics. He just wanted the math to work. And yet, by introducing quantization, he lit the first match in what would become a slow-burning fire. A fire that would eventually change our understanding of light, matter, and the nature of reality itself. This humble beginning, tucked away in a quiet paper published in 1900, did not shout its importance. There were no grand pronouncements, no sweeping declarations, just a tiny constant, a new way of thinking about energy, and a curious little fix to a problem that refused to go away. From that moment on, physics would never again feel completely finished. The photoelectric effect and duality. By the early 1900s, light was thought to be a well-understood phenomenon. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved as a wave, an elegant ripple in an electromagnetic field. It refracted, reflected, diffracted, and interfered just like any well-behaved wave. And after Max Planck's quiet introduction of energy quanta, most physicists assumed things would settle into a new, slightly adjusted normal. But then, a puzzle emerged involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect, and it worked like this. If you shine a light on a metal surface, electrons can be ejected from the metal. The idea made sense. Light transfers energy, and the energy knocks out electrons. No big deal. According to wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should be more effective at shaking out the electrons. That was the expectation, but it didn't happen. In experiments, scientists found something strange. Shining brighter light did not necessarily eject electrons with more energy. The most important thing was the frequency of the light. If the light's frequency was below a certain threshold, even very bright light produced no effect. No electrons were ejected. But above that threshold, even a dim beam could easily knock out electrons. The threshold was sharp, and it made no sense within the framework of classical wave theory. This little discrepancy turned into a full-blown mystery. Enter Albert Einstein. In 1905, the year often called his miracle year, Einstein published a paper that changed everything to explain the photoelectric effect. He proposed something bold. What if light wasn't just a wave? What if under certain circumstances it behaved like a particle, a tiny bundle of energy traveling in a straight line? Einstein suggested that light was made of discrete packets of energy, which he called light quanta, later known as photons. Each photon carried a specific amount of energy determined by its frequency. If a photon had enough energy, it could knock an electron out of the metal surface. If not, then no amount of photons, no matter how many or how bright, could do the job. It was like trying to open a locked door with a handful of keys, none of which fit. No matter how many you had, you couldn't get in. Einstein's idea directly built on Planck's earlier work, but went further. He didn't just use energy packets as a mathematical trick. He suggested that light itself was composed of these packets, not as a convenient fiction, but as a literal description of how light behaves. It was a revolutionary statement, and not everyone liked it. Many physicists clung to the wave model of light. After all, light clearly exhibited wave-like behavior. It diffracted around corners. It created interference patterns. If light was truly made of particles, how could it also act as a wave? Einstein didn't deny the wave-like nature of light. Instead, he proposed something even stranger. Light, he said, was both a wave and a particle. It could act as one or the other, depending on how you observed it. This duality wasn't just a strange trick of perception. It was fundamental to the very nature of light. Picture a beam of sunlight streaming through a window. It spreads and ripples like a wave, reflecting off dust and glass. But if you look closely, you'll find tiny quanta of energy, each with its own frequency, crashing into atoms, changing the world one collision at a time. This idea of wave-particle duality is one of the weirdest in all of physics. Not because it's complex, but because it challenges the very categories we use to describe reality. In the classical world, things are either particles or waves, not both, and certainly not whatever they feel like being, depending on the situation. But the quantum world doesn't ask for permission to make sense. Einstein's explanation of the photoelectric effect using photons not only matched the experimental results, but it did so beautifully. The energy of each photon depended on its frequency, as Planck had suggested, and this neatly explained why low-frequency light, no matter how intense, couldn't eject electrons. The individual photons simply didn't carry enough charge. The impact of this idea was immense. In 1921, Einstein was awarded the Nobel Prize in Physics, not for relativity as many assume, but for his explanation of the photoelectric effect. That's how significant this discovery was. The double-slit experiment, picture this. You set up a table, place a flashlight at one end, and cut two tiny slits in a piece of cardboard. You shine the flashlight through the slits and watch the pattern it makes on a screen behind them. Not very exciting, right? And yet, in this humble setup of two holes and a little bit of light, we find one of the most mind-bending experiments in all of science. The double-slit experiment has become a kind of legend in physics, not because it's complicated. In fact, it's almost ridiculously simple, but what it reveals is anything but. Some physicists have even joked that it's the most dramatic scientific experiment of all time, starring a flashlight and two holes in cardboard. Let's start with what we'd expect. In the world of classical physics, waves and particles behave very differently. A wave, like water or sound, spreads out. It interferes with itself. Imagine ocean waves passing through two holes in a barrier. The waves emerge on the other side and overlap, creating a pattern of peaks and troughs that can either amplify or cancel each other out. This is interference. It's well understood and predictable. Now, imagine particles like tiny rubber balls being shot at a wall with two holes. Some go through the left slit, some go through the right. They don't overlap or interfere. On a screen behind the slits, you'd expect to see two clusters of impact points right where the slits are. That's particle behavior. Straightforward, no surprises. So what happens when you do this with light? When scientists first sent light through the two slits, they expected it to behave like a wave, and it did. The light spread out and formed an interference pattern, a series of bright and dark bands on the screen, caused by the peaks of the waves overlapping and canceling each other out in certain spots. So far, so good. Light, as Maxwell had predicted, was behaving like a wave. But then things got weird. Using very sensitive equipment, researchers turned down the intensity of the light source to the point where they were sending a single photon at a time. A single photon is a particle, so you'd expect it to act like the little rubber balls. One at a time, you'd see it hit the screen in one of two places, either lined up with the left slit or with the right. Over time, as more and more photons hit the screen, you'd expect the same two clusters of dots to form, but they didn't. Instead, even when the photons were sent one by one, they still built up an interference pattern. The same pattern as when there was a constant beam of light. It was as if each single particle of light on its lonely journey through space was somehow passing through both slits at the same time and interfering with itself. This was utterly baffling. How could a single particle, which has no reason to split, go through two places at once? It defied all logical explanation, and it hinted at a profound, almost absurd truth about the quantum world. A single particle doesn't have a specific location. It exists as a kind of probability cloud, a wave function that spreads out and occupies every possible path. The wave function for the photon went through both slits, and on the other side, it interfered with itself, and only then, when it hit the screen, did that wave function collapse, and the particle's position become definite. The most bizarre part? When scientists tried to get clever and find out which slit the photon actually went through, the interference pattern vanished. If they placed a detector at one of the slits to observe its path, the act of observation seemed to change the particle's behavior. The photon no longer acted as a wave, it now acted like a particle. It went through one slit or the other, and the pattern on the screen reverted to the two-cluster pattern you'd expect from tiny rubber balls. The act of measurement seemed to force the particle to make a choice. It was as if the universe was saying, you can either know where it is or you can know what it does, but you can't know both. The experiment with two slits became the defining image of the quantum world, a place where particles aren't just one thing, but a blur of possibilities, where a particle can be in two places at once, and where the very act of looking seems to change what's there. The uncertainty principle. This is one of the most famous ideas in all of physics, and it's also one of the most misunderstood. At its core, the uncertainty principle, formulated by German physicist Werner Heisenberg, is not about our inability to measure things due to flawed instruments. It's about a fundamental built-in fuzziness in nature itself. The principle states that there are certain pairs of properties in a quantum system that you cannot know with perfect accuracy at the same time. The most famous pair is a particle's position and momentum. Momentum is a measure of its mass and velocity. According to the uncertainty principle, the more precisely you know a particle's position, the less you can possibly know about its momentum, and vice versa. Imagine an electron. If you want to know exactly where it is, you have to hit it with a photon, a particle of light. But to see a tiny electron, you need a high-energy photon with a short wavelength. That high-energy photon will knock the electron, changing its momentum in a way you can't predict. So, in the very act of knowing its position, you've disturbed its momentum, making it uncertain. The opposite is also true. If you know its momentum precisely, you have to use a low-energy photon that won't disturb it. But a low-energy photon has a long wavelength, which means it can't give you a precise reading of the electron's position. It's not a matter of a poor measurement, it's that the very act of measuring one property affects the other. It's a fundamental trade-off. This principle also explains why atoms don't collapse. You might wonder why electrons don't simply fall into the nucleus of an atom since opposite charges attract. But thanks to the uncertainty principle, electrons can't sit still. If an electron were to fall into the nucleus and stay there, its position would be perfectly known, which means its momentum would become infinitely uncertain. That would require infinite energy. Nature says no. So electrons hover not because they want to, but because quantum rules won't allow anything else. The uncertainty principle creates a kind of built-in resistance, a gentle pushback against absolute confinement. This strange limit also has consequences for measurements of energy and time, or angular momentum and orientation in each pair. Increasing precision in one means surrendering certainty in the other. It's a universal truth at the quantum level. And yet, there's something comforting about it too. Uncertainty in this sense is not chaos. It's not randomness run wild. It's a structured ambiguity, a kind of graceful fuzziness. It gives the universe its texture. It allows particles to tunnel through barriers, atoms to be stable, and chemistry to happen. Without it, reality might be too rigid to support life at all. So much of science has been about finding certainty, predicting, measuring, knowing. Heisenberg's insight flipped that desire on its head. He showed that some aspects of nature will always remain just out of reach. And that's not a failure, it's just how things are. In a strange way, the uncertainty principle invites us to make peace with not knowing, to sit quietly with the blur and appreciate the softness of what lies beneath the surface. It's a reminder that the deepest truths are not always sharp-edged, but cloudy, rippling, and unresolved. And perhaps that's exactly why they're so beautiful. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails. A light switch is on or off. Your tears are hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division of states breaks down completely. Objects at the smallest scales don't always pick a side. They can hover in a strange in-between, a blend of all possible outcomes. This is the realm of quantum superposition. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a clear trajectory. You may not know whether it's heads or tails until it lands, but it is one or the other the whole time. It's just hidden from you. Quantum systems don't work that way. In the quantum world, if you flip a quantum coin, it doesn't secretly land on one side while you're not looking. Instead, it enters a state of superposition, a weighted combination of both heads and tails at once. It isn't undecided. It isn't switching quickly between the two. It is genuinely physically in a state that is both until you observe it. And when you do, when you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face and your measurement becomes real. But before you looked, it wasn't just unknown, it was both. That's a hard pill to swallow, and it's not just counterintuitive, it's deeply weird. Superposition was first introduced as a way to describe the behavior of quantum particles like electrons and photons. These particles, rather than following predictable paths, exist as wave functions, mathematical expressions that describe probabilities. Each possible state, a spin pointing up or down, a photon going left or right, is part of the equation. And all those possibilities coexist until a measurement selects one. You might picture it like a foggy landscape of outcomes. The particle isn't walking a path, it's more like it's spread out, smearing itself across every possible route it could take. When you interact with it, that fog suddenly snaps into a single location. A specific outcome like lightning illuminating one hilltop in the mist. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, And a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics tells us that until the atom is observed, it exists in a superposition of decayed and not decayed states. And so, by extension, the cat is both alive and dead until someone opens the box. This wasn't meant to be taken literally. Erwin Schrödinger was highlighting the absurdity of applying quantum rules to large objects, but the idea struck a chord. It painted superposition not just as an abstract idea, but as something with deeply strange implications for what reality is. And yet, despite all the weirdness, superposition is not a flaw in the theory. It's not some bizarre loophole that physicists tolerate. It is one of the most powerful features of quantum mechanics. In fact, much of modern quantum technology depends on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo, every song, every message is encoded using combinations of these two states. Quantum computers use qubits instead, and a qubit, unlike a regular bit, can exist in a superposition of both 0 and 1 at the same time. It's not switching between them, it's genuinely in a mixture of both. This means that a single qubit holds more information than a classical bit, and when multiple qubits are entangled, they can represent a vast number of states simultaneously. This allows quantum computers to perform certain calculations far more efficiently than classical ones. Its not-M superposition also appears in quantum cryptography, where it helps ensure that information can't be intercepted without being noticed. In quantum sensing, it allows scientists to detect extremely small changes in magnetic or gravitational fields. These aren't sci-fi dreams. There are real technologies being developed right now, but there's a twist. Superposition is delicate. Quantum systems are easily disturbed. The slightest interaction with the environment, stray photons, vibrations, even air molecules can collapse the wave function. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It's like trying to balance a feather on the tip of a pencil while someone's sneezing. In the next room, the superposition vanishes the moment the system interacts with the outside world. That fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise and isolated conditions. They give us access to probabilities, not certainties, and ask us to rethink what it means to say that something is. It also leads to a deeper philosophical question. If particles can exist in multiple states, is that reality or just a reflection of what we know? Some interpretations suggest that the wave function represents knowledge, our best guess about a system until we measure it. Others say the wave function is physically real and the particle truly is in multiple states until it's forced to choose. Either way, quantum superposition invites us to loosen our grip on classical logic. It tells us that opposites can coexist, that a system can be this and that, here and there, yes and no, all at once. That reality at its core is not a single thread, but a tapestry of possibilities overlapping and unresolved until observation pulls one strand loose. It's strange. It's unimagined you have two gloves, one left-handed and one right-handed. You put each glove into a separate box and send one to the other side of the world. You don't know which box contains which glove. But the moment you open one and see a left-handed glove, you instantly know the other must be right-handed. It's not mysterious, it's just logic. The gloves were always one left, one right. No drama there. But quantum entanglement isn't like that. Entangled particles aren't like pre-packed gloves. They're more like a pair of gloves that don't decide which hand they are until after you open one of the boxes. And whichever one you open first somehow tells the other how to behave instantly, no matter how far apart they are. It's not just that the outcome is correlated, it's that the properties don't seem to exist until the moment you measure one of them, and the act of measuring one instantly affects the other. This is the phenomenon of quantum entanglement, and it is one of the strangest, most baffling features of the quantum world. Here's how it works. When two particles interact in a certain way, by being created together, colliding, or otherwise becoming connected, they can become entangled. That means their quantum states become linked. Whatever happens to one in a very real sense affects the other, even when they are separated by great distances. Imagine creating two entangled photons whose polarizations are uncertain until measured. One might end up polarized vertically, the other horizontally, but they don't decide ahead of time who gets which. They stay in a shared quantum state. Oh, superposition of all possibilities. Only when you measure one does the outcome become definite, and at that moment the other state becomes definite too. Instantly, no signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's say it's in Tokyo, responds at that very moment, as though the universe just updated both of them simultaneously. This is what Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed firmly in locality, the idea that physical processes at one location can't instantly affect things far away. It's a cornerstone of relativity. Nothing, not even information, travels faster than light. The idea that two particles could coordinate outcomes instantaneously without exchanging a signal made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics. They argued that if quantum mechanics allows for such instantaneous connections, it must be missing something. Some hidden variables tucked behind the scenes, determining the outcomes all along. To Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables, they never showed up. In the 1960s, physicist John Bell devised a testable mathematical inequality, now known as Bell's theorem, that could distinguish between quantum predictions and hidden variable theories. And when physicists performed these experiments again and again, quantum mechanics won. Entangled particles do behave in ways that can't be explained by local hidden variables. The results are random yet perfectly correlated. It's as if the particles share a private script, one that remains unwritten until the curtain rises, and they improvise together with eerie perfect timing. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality, and thankfully nature prevents it. While entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You can't control what results you get when you measure your particle, which means you can't encode information in it. The instant connection is real, but it can't be used for communication. It's like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow when one person flips heads, the other always flips tails, and neither of them knows which it will be until they flip. They aren't sending messages. They're just in sync in a way that defies space. What's truly strange is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent, or a light year, and the entanglement would remain. There's no known limit. In fact, physicists have entangled particles over distances of hundreds of kilometers using satellites, and the results continue to uphold quantum theory. But what exactly is entanglement? Is it a kind of invisible tether, a shared identity across space, a subtle form of information smeared between particles? The truth is, no one's completely sure. Different interpretations of quantum mechanics offer different perspectives. Some see entanglement as a reflection of information, what we know about the system, not the system itself. Others see it as evidence of a deep, non-local fabric to reality. There's even a school of thought that entanglement isn't just a quirky quantum trick, but a fundamental feature of space and time themselves. Some researchers have proposed that space-time, the very geometry of the universe, might emerge from networks of entanglement between tiny quantum bits. If that's true, entanglement isn't something that happens in space. It's what holds space together. That's a bold idea and one still under investigation, but it hints at just how central entanglement may be, not just to particles, but to the nature of reality. And like many quantum ideas, it's not just theoretical. Entanglement has practical applications. It's the foundation for quantum teleportation, not the Star Trek kind, but the real-world transfer of quantum states from one place to another. It also underlies quantum key distribution, a method of secure communication that guarantees privacy. If an eavesdropper tries to intercept the key, the entanglement is disturbed and the interference is immediately detectable. In quantum computing, entanglement allows for complex operations involving many qubits that can't be reduced to simple individual actions. It's part of what gives quantum computers their power, not just more speed, but more interconnection, a kind of parallelism that ordinary computers can't match. So this spooky action, once a source of deep unease, is now a cornerstone of cutting-edge technology. Einstein may have disliked it, but even he couldn't deny its mathematical consistency. And while relativity and quantum mechanics still haven't been fully unified, both remain astonishingly successful in their respective realms. Entanglement reminds us that the universe is not simply a collection of independent objects bouncing around. It is a deeply interconnected web where even distant elements can be parts of a shared whole. Where separateness is at times an illusion, it's not something we see in daily life. You don't wake up entangled with your neighbor or find your coffee reflecting the state of someone else's spoon. But at the tiniest levels, this silent partnership between particles is quietly humming away everywhere all the time. And maybe that's the strangest part of all, that even in a universe of stars and silence, of vast distance and emptiness, there are still echoes of togetherness. Instant. In Schrödinger's cat, there are few animals in science more famous than Schrödinger's cat. This curious feline has become the unofficial mascot of quantum physics, a creature trapped in a thought experiment so peculiar that it's often mistaken for satire. And in a way, it is. It was never meant to be taken literally, but like all good metaphors, it touches on something deeper, a quiet discomfort at the heart of quantum mechanics. The story begins in the 1930s when physicists were grappling with what quantum theory actually meant. The math worked, the predictions were accurate, but what was it saying about the world? Was the wave function a real thing? Did particles really exist in multiple states until they were measured? Or was this just a tool for calculating outcomes? Erwin Schrödinger, already famous for his elegant quantum equation, was deeply skeptical of how far some physicists were willing to push the idea of superposition, especially when it came to measurement. In his view, there was something fishy about applying the same rules that governed electrons to everyday objects, like say a cat. So he posed a question, a dark, playful question. What happens if you take the weirdness of quantum mechanics and scale it up to something you can hold in your arms? Imagine a sealed box. Inside the box is a cat. Alongside the cat is a tiny radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays, something quantum mechanics tells us happens at random. The Geiger counter detects it, the trigger breaks the vial, and the poison is released. The cat tragically dies. But here's the twist. Quantum theory tells us that until we observe the atom, it exists in a superposition of both decayed and not decayed states. And so, by extension, the entire system, the detector, the poison, and yes, the cat should also be in a superposition. The cat is both alive and dead, not metaphorically, literally, at least according to some interpretations. In our everyday experience, things tend to be in one state or another. A coin lands heads or tails. A light switch is on or off. Your tears are hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division of states breaks down completely. Objects at the smallest scales don't always pick a side. They can hover in a strange in-between, a blend of all possible outcomes. This is the realm of quantum superposition. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a clear trajectory. You may not know whether it's heads or tails until it lands, but it is one or the other the whole time. It's just hidden from you. Quantum systems don't work that way. In the quantum world, if you flip a quantum coin, it doesn't secretly land on one side while you're not looking. Instead, it enters a state of superposition, a weighted combination of both heads and tails at once. It isn't undecided. It isn't switching quickly between the two. It is genuinely physically in a state that is both until you observe it. And when you do, when you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face and your measurement becomes real. But before you looked, it wasn't just unknown, it was both. That's a hard pill to swallow. And it's not just counterintuitive, it's deeply weird. Superposition was first introduced as a way to describe the behavior of quantum particles like electrons and photons. These particles, rather than following predictable paths, exist as wave functions, mathematical expressions that describe probabilities. Each possible state, a spin pointing up or down, a photon going left or right, is part of the equation. And all those possibilities coexist until a measurement selects one. You might picture it like a foggy landscape of outcomes. The particle isn't walking a path, it's more like it's spread out, smearing itself across every possible route it could take. When you interact with it, that fog suddenly snaps into a single location. a specific outcome like lightning illuminating one hilltop in the mist. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics tells us that until the atom is observed, it exists in a superposition of decayed and not decayed states. And so, by extension, the cat is both alive and dead until someone opens the box. This wasn't meant to be taken literally. Erwin Schrödinger was highlighting the absurdity of applying quantum rules to large objects. But the idea struck a chord. It painted superposition not just as an abstract idea, but as something with deeply strange implications for what reality is. And yet, despite all the weirdness, superposition is not a flaw in the theory. It's not some bizarre loophole that physicists tolerate. It is one of the most powerful features of quantum mechanics. In fact, much of modern quantum technology depends on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo, every song, every message is encoded using combinations of these two states. Quantum computers use qubits instead, and a qubit, unlike a regular bit, can exist in a superposition of both 0 and 1 at the same time. It's not switching between them, it's genuinely in a mixture of both. This means that a single qubit holds more information than a classical bit, and when multiple qubits are entangled, they can represent a vast number of states simultaneously. This allows quantum computers to perform certain calculations far more efficiently than classical ones. It's not M-superposition also appears in quantum cryptography, where it helps ensure that information can't be intercepted without being noticed. In quantum sensing, it allows scientists to detect extremely small changes in magnetic or gravitational fields. These aren't sci-fi dreams. There are real technologies being developed right now, but there's a twist. Superposition is delicate. Quantum systems are easily disturbed. The slightest interaction with the environment, stray photons, vibrations, even air molecules can collapse the wave function. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It's like trying to balance a feather on the tip of a pencil while someone's sneezing. In the next room, the superposition vanishes the moment the system interacts with the outside world. That fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise and isolated conditions. They give us access to probabilities, not certainties, and ask us to rethink what it means to say that something is. It also leads to a deeper philosophical question. If particles can exist in multiple states, is that reality or just a reflection of what we know? Some interpretations suggest that the wave function represents knowledge, our best guess about a system until we measure it. Others say the wave function is physically real, and the particle truly is in multiple states until it's forced to choose. Either way, quantum superposition invites us to loosen our grip on classical logic. It tells us that opposites can coexist, that a system can be this and that, here and there, yes and no, all at once. That reality at its core is not a single thread, but a tapestry of possibilities overlapping and unresolved until observation pulls one strand loose. It's strange. It's unimagined you have two gloves, one left-handed and one right-handed. You put each glove into a separate box and send one to the other side of the world. You don't know which box contains which glove. But the moment you open one and see a left-handed glove, you instantly know the other must be right-handed. It's not mysterious. It's just logic. The gloves were always one left, one right. No drama there. But quantum entanglement isn't like that. Entangled particles aren't like pre-packed gloves. They're more like a pair of gloves that don't decide which hand they are until after you open one of the boxes. And whichever one you open first somehow tells the other how to behave instantly, no matter how far apart they are. It's not just that the outcome is correlated, it's that the properties don't seem to exist until the moment you measure one of them, and the act of measuring one instantly affects the other. This is the phenomenon of quantum entanglement, and it is one of the strangest, most baffling features of the quantum world. Here's how it works. When two particles interact in a certain way, by being created together, colliding, or otherwise becoming connected, they can become entangled. That means their quantum states become linked. Whatever happens to one in a very real sense affects the other even when they are separated by great distances. Imagine creating two entangled photons whose polarizations are uncertain until measured. One might end up polarized vertically, the other horizontally, but they don't decide ahead of time who gets which. They stay in a shared quantum state, superposition of all possibilities. Only when you measure one does the outcome become definite, and at that moment, the other state becomes definite too, instantly. No signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's say it's in Tokyo, responds at that very moment as though the universe just updated both of them simultaneously. This is what Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed firmly in locality, the idea that physical processes at one location can't instantly affect things far away. It's a cornerstone of relativity. Nothing, not even information, travels faster than light. The idea that two particles could coordinate outcomes instantaneously without exchanging a signal made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics. They argued that if quantum mechanics allows for such instantaneous connections, it must be missing something, some hidden variables tucked behind the scenes, determining the outcomes all along. To Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables, they never showed up. In the 1960s, physicist John Bell devised a testable mathematical inequality, now known as Bell's theorem, that could distinguish between quantum predictions and hidden variable theories. And when physicists performed these experiments again and again, quantum mechanics won. Entangled particles do behave in ways that can't be explained by local hidden variables. The results are random yet perfectly correlated. It's as if the particles share a private script, one that remains unwritten until the curtain rises, and they improvise together with eerie perfect timing. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality, and thankfully nature prevents it. While entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You can't control what results you get when you measure your particle, which means you can encode information in it. The instant connection is real, but it can't be used for communication. It's like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow when one person flips heads, the other always flips tails, and neither of them knows which it will be until they flip. They aren't sending messages. They're just in sync in a way that defies space. What's truly strange is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent, or a light year, and the entanglement would remain. There's no known limit. In fact, physicists have entangled particles over distances of hundreds of kilometers using satellites, and the results continue to uphold quantum theory. But what exactly is entanglement? Is it a kind of invisible tether, a shared identity across space, a subtle form of information smeared between particles? The truth is, no one's completely sure. Different interpretations of quantum mechanics offer different perspectives. Some see entanglement as a reflection of information, what we know about the system, not the system itself. Others see it as evidence of a deep, non-local fabric to reality. There's even a school of thought that entanglement isn't just a quirky quantum trick, but a fundamental feature of space and time themselves. Some researchers have proposed that space-time, the very geometry of the universe, might emerge from networks of entanglement between tiny quantum bits. If that's true, entanglement isn't something that happens in space. It's what holds space together. That's a bold idea and one still under investigation, but it hints at just how central entanglement is, maybe not just to particles, but to the nature of reality. And like many quantum ideas, it's not just theoretical. Entanglement has practical applications. It's the foundation for quantum teleportation, not the Star Trek kind, but the real-world transfer of quantum states from one place to another. It also underlies quantum key distribution, a method of secure communication that guarantees privacy. If an eavesdropper tries to intercept the key, the entanglement is disturbed and the interference is immediately detectable. In quantum computing, entanglement allows for complex operations involving many qubits that can't be reduced to simple individual actions. It's part of what gives quantum computers their power, not just more speed, but more interconnection, a kind of parallelism that ordinary computers can't match. So this spooky action, once a source of deep unease, is now a cornerstone of cutting-edge technology. Einstein may have disliked it, but even he couldn't deny its mathematical consistency. And while relativity and quantum mechanics still haven't been fully unified, both remain astonishingly successful in their respective realms. Entanglement reminds us that the universe is not simply a collection of independent objects bouncing around. It is a deeply interconnected web where even distant elements can be parts of a shared whole. Where separateness is at times an illusion, it's not something we see in daily life. You don't wake up entangled with your neighbor or find your coffee reflecting the state of someone else's spoon. But at the tiniest levels, this silent partnership between particles is quietly humming away everywhere all the time. And maybe that's the strangest part of all, that even in a universe of stars and silence, of vast distance and emptiness, there are still echoes of togetherness, instant in Schrödinger's cat. There are few animals in science more famous than Schrödinger's cat. This curious feline has become the unofficial mascot of quantum physics, a creature trapped in a thought experiment so peculiar that it's often mistaken for satire. And in a way, it is. It was never meant to be taken literally, but like all good metaphors, it touches on something deeper, a quiet discomfort at the heart of quantum mechanics. The story begins in the 1930s when physicists were grappling with what quantum theory actually meant. The math worked, the predictions were accurate, but what was it saying about the world? Was the wave function a real thing? Did particles really exist in multiple states until they were measured? Or was this just a tool for calculating outcomes? Erwin Schrödinger, already famous for his elegant quantum equation, was deeply skeptical of how far some physicists were willing to push the idea of superposition, especially when it came to measurement. In his view, there was something fishy about applying the same rules that governed electrons to everyday objects, like say a cat. So he posed a question, a dark, playful question. What happens if you take the weirdness of quantum mechanics and scale it up to something you can hold in your arms? Imagine a sealed box. Inside the box is a cat. Alongside the cat is a tiny radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays, something quantum mechanics tells us happens at random. The Geiger counter detects it, the trigger breaks the vial, and the poison is released. The cat tragically dies. But here's the twist. Quantum theory tells us that until we observe the atom, it exists in a superposition of both decayed and not decayed states. And so, by extension, the entire system, the detector, the poison, and yes, the cat should also be in a superposition. The cat is both alive and dead, not metaphorically, literally, at least according to some interpretations. Of course, no one has actually put a cat in a quantum box. Schrödinger wasn't proposing an experiment, he was making a point. He found it absurd to think that a cat, an animal with whiskers, warmth, and a clear preference for naps, could exist in such a blurry, undefined state. It wasn't just strange, it was nonsense. And yet the idea stuck partly because it captured the essence of quantum indeterminacy in a single unforgettable image. A cat that is both dead and alive until the box is opened. That's a powerful way to express what it means for a system to remain unmeasured. It's not about indecision, it's about possibility. Until observation collapses the wave function, the system contains every outcome, all futures, all states. Simultaneously, Schrödinger's cat isn't really about cats. It's about what we're allowed to say about the world before we've looked. In quantum mechanics, observation plays a central role. Before you measure a system, it exists in a cloud of probabilities. Each possible state is encoded in the wave function, but the moment you interact with it in a way that extracts information, that cloud collapses. The system picks a state. 1. Possibility becomes real, all others vanish. But here's the tricky part. What exactly counts as a measurement? Is it the presence of a conscious observer, a mechanical detector, an interaction with the environment? Different interpretations give different answers, and that ambiguity is part of why the cat still gets so much attention. It forces us to confront the fact that quantum theory, while breathtakingly successful in predicting outcomes, is oddly silent about what's really happening in between. Some physicists lean on the Copenhagen interpretation, which essentially says don't worry about it. The wave function tells us everything we can know, and measurement simply reveals what's already latent in the system. Others prefer the many worlds view, where the cat is both alive and dead in separate branching universes, and opening the box doesn't collapse the wave function. It merely selects your path through the multiverse. There's also the decoherence approach, which argues that interaction with the environment naturally filters out superpositions, leaving systems that appear classical. In this view, the cat is never truly in a limbo state, just entangled with so many environmental variables that we can't track them all. The superposition becomes inaccessible, not non-existent. Each perspective carries its own philosophical baggage, but all agree on this. Quantum systems do not behave like miniature classical objects. They don't sit still and wait to be discovered. They evolve probabilistically in compil. So what does this mean for the cat? It means the box isn't just a container, it's a boundary between the quantum and classical worlds. A stage on which the rules of physics twist into something weirder, where questions like, is the cat alive? Don't have simple answers. Instead, we have to say the cat is in a superposition of states, alive and dead, until we open the box and collapse that ambiguity into something definite. And that's what makes the cat a perfect metaphor for unmeasured systems. In the quantum world, systems evolve according to the Schrödinger equation, but that evolution doesn't pick a path. It explores all possible paths at once. An electron doesn't travel from point A to point B. It spreads through every route, every detour, until we observe it and reduce that blur to a single outcome. The cat in the box is just a macroscopic way of expressing that. The difference is scale, not principle, and that's what troubled Schrödinger. If the theory truly applies to everything, then at some level Eve, which leads to one final somewhat unsettling question. What if the observer is part of the system? If opening the box collapses the cat's wave function, what collapses ours? Where does the observer line stop? Are we just another link in a long quantum chain, collapsing probabilities as we go? Or are we simply riding the wave, surfing on probabilities, never quite sure where the next collapse will take us? In the end, Schrödinger's cat isn't just about life and death. It's about knowledge and the strange dance between reality and observation. It's about what it means to say something is when the very act of saying so might change the outcome. It's a reminder that in the quantum world, certainty is rare, clarity is conditional, and sometimes the universe waits for us to peek inside the box. In the everyday world, walls are pretty straightforward. If you throw a tennis ball at a wall, and it doesn't have enough energy to get through, it bounces off. Simple, predictable. The universe says, nice try, and your ball obeys the rules of classical physics like a well-behaved object. But in the quantum world, predictability takes a holiday. In this strange realm, a particle can hit a wall, not have enough energy to pass through, and yet still show up on the other side. No smashing, no breaking, no squeezing through cracks. It simply appears as if it decided the obstacle wasn't quite as solid as it looked. This phenomenon is called quantum tunneling, and it's one of those effects that makes you blink, rub your eyes, and wonder if the laws of physics are having a laugh. But tunneling is very real. It's measurable, predictable, and fundamental to how the universe works. And surprisingly, it all comes down to probability. To understand tunneling, we need to revisit the concept of wave functions. In quantum mechanics, particles like electrons aren't just little dots zooming around. They're described by wave functions that represent a spread of possible positions. These waves can extend across space, fading gradually instead of stopping abruptly. This means that even if there's a region the particle technically shouldn't be able to reach, the wave function might still stretch into that forbidden zone, albeit faintly. Now, imagine a particle approaching a barrier, a region with more energy than the particle itself has. In classical physics, this would be a hard stop. Game over. But the quantum wave function doesn't vanish at the barrier. It tapers off like a whisper fading through a wall. And if the wall isn't too wide or too tall, that whisper can make it to the other side. The particle might not have enough energy to climb over the barrier, but its wave function can tunnel through. And if part of the wave function makes it to the other side, there's a small but non-zero probability that the particle itself will show up there too. But it's not magic, it's math. This idea sounds abstract, but it has very concrete consequences, especially when you shrink your thinking down to the atomic scale. Take radioactive decay, for example. Some atomic nuclei are unstable, and one of the ways they become stable is by ejecting particles like alpha particles made of 2 protons and 2 neutrons. These particles are trapped inside the nucleus by a powerful nuclear barrier. According to classical physics, they don't have enough energy to escape, but they do escape constantly. And quantum tunneling is the reason why inside the nucleus, the alpha particle's wave function stretches toward the edge of the nuclear potential barrier. Even though it's unlikely, there's always a chance the particle will tunnel through. Over time, that small probability adds up, and eventually the particle pops out. That's radioactive decay in action. Without tunneling, many elements would never decay, and nuclear physics, as we know it, would grind to a halt. Tunneling is also critical for the most important energy source in the universe, nuclear fusion. In the core of stars, hydrogen nuclei are crushed together under immense pressure and heat. But even with those extreme conditions, they don't really have enough energy to overcome the electrostatic repulsion between their positively charged protons. According to classical calculations, fusion shouldn't happen nearly as often as it does. Yet stars shine, and tunneling explains why. At those high temperatures, hydrogen nuclei get close enough for their wave functions to overlap. There's a tiny chance that one will tunnel through the repulsive barrier and fuse with another. Multiply that tiny chance by the unthinkable number of particles in a star, and you get a brilliant sustained fusion process, the furnace that powers everything from sunshine to supernovas. And it's not just distant stars that benefit from tunneling. We use it right here on Earth, in labs, in factories, even in experimental computers. One elegant example is the Scanning Tunneling Microscope, or STM. This device allows scientists to visualize surfaces at the level of individual atoms. It works by bringing an ultra-sharp tip extremely close to the surface of a material, just a few nanometers away. At that distance, electrons can tunnel between the tip and the surface. By measuring this tunneling current, the microscope builds up an incredibly detailed map of the atomic landscape. What's remarkable is that the STM doesn't touch the atoms. Its imaging is relying entirely on tunneling, on the ability of electrons to slip quietly through empty space, across a gap, and into a detector. This non-contact technique gives scientists a way to peer into the quantum terrain with stunning precision. Tunneling is also at the heart of certain types of electronic components, like tunnel diodes and quantum dots. And it's a looming factor in the future of computing. As we shrink transistors to ever smaller sizes, we're running into quantum limits. At nanometer scales, electrons can tunnel through barriers that were once considered solid. It's as if the walls in our circuitry are starting to let particles sneak through when they're not supposed to. This presents both challenges and opportunities. On one hand, it creates noise and unpredictability in traditional electronics. On the other hand, it opens the door to quantum technologies that use tunneling rather than fight against it. At its core, tunneling teaches us something profound about the nature of reality. We often think of the world as made of hard boundaries. A particle can go here but not there. A wall is a wall. But the quantum world is more nuanced. Barriers are not impenetrable. They are probabilistic. They are suggestions, not absolutes. And while we might find that unsettling, it's also strangely elegant. Because of tunneling, particles are not confined to the straight paths we imagine. They can cheat, slip, blur through the cracks of logic. They remind us that the universe is not a machine made of perfect gears, but a shimmering tapestry of likelihoods and possibilities. The tennis ball still bounces off the wall, but the electron, the alpha particle, the photon, they might just glance at that same wall and say, "I think I'll take the shortcut." And somehow, nature lets them. In everyday life, we think of nothing as, well, nothing. The absence of stuff, an empty room, a blank sheet of paper, the space under your bed where socks mysteriously disappear. And when we extend that idea to physics, we often picture the vacuum of space as a perfect void, a cold, silent expanse with absolutely nothing in it. But in quantum physics, nothing is never really empty. What we call the quantum vacuum is a restless, jittering stage. It's not filled with atoms or light or sound, but it's far from blank. Even when all particles have been removed and no fields are actively doing anything, the vacuum still seethes with energy. At the smallest scales, space is alive with invisible activity. Waves rising and falling, particles flickering in and out of existence. It is like the hum beneath silence, the glow behind darkness, and it all starts with uncertainty. Heisenberg's uncertainty principle doesn't just apply to particles' position and momentum, it also applies to energy and time. That means that even in a region of space where energy should be zero, the energy can briefly fluctuate. These fluctuations give rise to virtual particles which appear spontaneously, hang around for a fleeting moment, and then vanish as if they never existed. They're called virtual not because they're imaginary, but because they can't be directly observed, only inferred through their effects. These quantum blips might seem like a mathematical curiosity, but they have very real consequences. One of The most striking examples is something called the Casimir effect. It's one of those rare phenomena that lets us see the quantum vacuum doing something tangible, something measurable. Here's how it works. Imagine placing two very thin, perfectly conducting metal plates extremely close together in a vacuum, just a few nanometers apart. According to classical physics, nothing should happen. There's no air between the plates, no forces acting on them, just an empty gap, but quantum mechanics says otherwise. Because the space between the plates is so small, only certain wavelengths of virtual particles can exist there, ones that fit neatly between the boundaries. Outside the plates, however, there's no such restriction. The result, there's slightly more pressure from virtual particles outside the plates than between them, and this imbalance creates a force that pushes the plates together. That's the Casimir. This vacuum energy isn't just limited to quirky lab setups. It plays a role across the entire universe. In cosmology, there's the idea of vacuum energy density, the notion that the energy of empty space might be responsible for the accelerating expansion of the universe. We call this mysterious force dark energy, and while we don't fully understand it, the concept of a quantum vacuum buzzing with energy might be a big part of the puzzle. But there's a catch. The predicted energy of the quantum vacuum according to quantum field theory is enormous. If we tried to calculate the total vacuum energy of the universe using what we know from particle physics, we'd get a number that's wildly larger, like 120 orders of magnitude larger than what we actually observe. This is often called the worst prediction in physics, and no one has quite figured out how to fix it. But it highlights just how complex and surprising the vacuum really is. Back at the quantum scale, virtual particles also play a supporting role in other strange phenomena. In quantum electrodynamics, for instance, the interaction between charged particles is partly mediated by the constant exchange of virtual photons. These exchanges give rise to the electromagnetic force as we experience it. Even the mass of particles like protons is affected by the swarm of virtual quarks and gluons flickering around inside them. What we think of as stable solid matter is really the result of constant interactions with this invisible fluctuating vacuum. And while these particles appear and disappear faster than we can measure, their influence is everywhere. They slightly alter the energy levels of electrons in atoms. They contribute to the magnetic moment of particles. They're woven into the fabric of every interaction, and this might sound like science fiction, but it's been tested. When we correct our calculations to include vacuum fluctuations, like in the famous Lamb shift observed in hydrogen atoms, we find that the predictions match reality with breathtaking accuracy. The math is weird, the concepts are wild, but the results are solid. In a way, the quantum vacuum is the most fundamental field of all. Every other field, electromagnetic, gravitational, nuclear, exists within it. They ripple and hum against its background like instruments playing on top of a bass line that never stops. Some physicists even suspect that the vacuum holds clues to deeper truths. Could it be the source of all structure in the universe? Might it contain information about quantum gravity, or even about space-time itself? These are open questions, but one thing is clear. The vacuum is not a passive backdrop. It's active, it's structured, it's full of potential. Even in the coldest regions of space, where matter is scarce and starlight is a memory, the quantum vacuum is still there, vibrating, jittering, whispering the rules of existence to anything, willing to listen. It's humbling to think that nothing is never truly nothing, that even in apparent stillness, the universe teems with hidden activity, in the pauses between moments, in the gaps between particles, in the silence between stars. Something is always happening. We live not on a quiet stage, but on one that murmurs beneath our feet. And while we may not hear it with our ears, physics has found the instruments to listen. The vacuum hums, the particles flicker, and reality dances to a rhythm we've only just begun to understand. The collapse of the wave function. In the quantum world, reality doesn't always behave like a story with a clear beginning, middle, and end. Particles don't just travel in straight lines. They drift in clouds of probability. They superpose, entangle, and sometimes tunnel their way through things that should be solid. But perhaps the most mysterious twist in this quantum tale comes when we ask a very human question. What happens when we look? This simple act of observing, of measuring seems to trigger something dramatic, a shift, a change in the very nature of the quantum system. This is known as wave function collapse. Before measurement, a particle like an electron or a photon is described by its wave function, a mathematical object that holds all the possible outcomes of where it could be or how it might behave. That electron isn't in one place, it's in a blend of many possible places. Its spin isn't up or down, it's both. Its path isn't chosen, it's all of them at once. The wave function is a shimmering probabilistic fog. But then you measure it. You fire up your detector, you ask, where is it? And in that instant, the wave function collapses, the fog condenses. All those swirling possibilities snap into a single reality. The electron is suddenly there in one precise spot. Its spin is up or down, not both. And this collapse doesn't seem to happen gradually. It's not a slow fading of possibilities. It's abrupt, binary. One moment the system is in superposition, the next it's locked into a definite state, as if the universe, after much hesitation, makes a final decision the moment we check. That's weird enough on its own, but it gets weirder because no one knows exactly what causes the collapse. Is it the physical interaction with a measuring device? Is it the transfer of information? Is it consciousness, a camera, a fly buzzing past the lab? The truth is, the collapse of the wave function, though central to quantum theory, is not well understood. In fact, it might be the biggest mystery in all of modern physics. Different interpretations of quantum mechanics try to answer the question in different ways. The most traditional view is the Copenhagen interpretation championed by Niels Bohr and Werner Heisenberg. In this view, the wave function is not a real physical object, it's just a tool for predicting probabilities. And collapse happens when a measurement is made, when we gain information. Before that, asking about what's really happening isn't meaningful. The electron isn't somewhere waiting to be found. It simply isn't anywhere in particular until we look. It's a practical approach. It makes the math work, but it leaves many scientists unsatisfied because it doesn't really explain what measurement is or why the wave function must collapse at all. Then there's the many worlds interpretation, which throws collapse out the window entirely. According to this idea, the wave function never collapses. Instead, every possible outcome happens, just not in your universe. Measure an electron spin and the universe splits. In one version, it's spin up. In another, spin down. You only experience one of those outcomes, but the others still exist, unfolding in parallel. No randomness, no collapse, just branching realities. It's a bold idea and surprisingly consistent with quantum math, but it comes at the cost of multiplying universes like cosmic confetti. Every measurement, every interaction, every choice, a never-ending spray of realities. It's elegant in one sense, absurd in another. Other interpretations aim to make collapse feel more real. In the objective collapse theories, the wave function is a physical thing that collapses spontaneously, randomly without measurement. It's just that measurement increases the chance of collapse. These theories introduce new rules or even new physics to explain when and how collapse happens. They're still being tested, but they offer an intriguing possibility that wave function collapse might be something nature does, not just something we see. Then there's cubism, a more recent and radical view. It suggests that the wave function doesn't describe the system at all. It describes our beliefs about the system. It's a personal, subjective tool for predicting outcomes. And collapse isn't a physical event, but a mental update, like learning, a new fact and revising your expectations. Reality doesn't change. You do. Some physicists find that refreshing. Others find it deeply unsatisfying. After all, shouldn't physics be about the universe, not our opinions? The Copenhagen interpretation, there's also the role of decoherence, which doesn't explain collapse directly but helps describe how superpositions seem to vanish in large systems. When a quantum system interacts with its environment, even just a few stray photons, it becomes entangled with the world around it. That entanglement causes the interference patterns we associate with superpositions to disappear. To us, the system looks like it collapsed, even though it hasn't truly picked a state. Decoherence explains why cats don't stay both alive and dead. But it stops short of saying how one outcome becomes real. And there we sit. More than a century after the birth of quantum theory, wave function collapse remains a ghost in the machine. The math works brilliantly. We can predict outcomes with incredible precision, but what exactly collapses? When? Why? Is collapse even real, or are we just seeing the limits of our own understanding and there's no shortage of ideas? Some researchers believe we need a new theory of measurement or a deeper theory of reality that goes beyond quantum mechanics. Others are content with the ambiguity. They say the predictions work and the rest is philosophy. But philosophy matters especially here because the question of wave function collapse isn't just about particles, it's about what the universe is. Is reality fundamentally probabilistic? Is it observer dependent? Is it constantly branching? Is it shaped by information, by consciousness, by something we've yet to discover? And how much can we ever really know? You can think of collapse as the moment the quantum world tips into the classical, a kind of phase change like water freezing into ice. But unlike water, the rules of this transformation are murky. We don't know the temperature. We don't know the pressure. We just know that at some point the fog becomes a shape and possibility becomes presence. It's easy to get lost in the metaphors. Is the wave function a veil, a dream, a menu of futures waiting to be chosen? Perhaps it's all of those and none. Perhaps what collapses is not the wave function itself, but our illusion that the world must always be definite, always be one thing or another. Maybe the universe is content being undecided. Maybe we're the ones who insist on conclusions. What happens when we measure? Maybe the better question is, what do we think happens? And are we prepared for the answer to be stranger than we hoped, but truer than we imagined? If quantum physics had a hometown, it would probably be Copenhagen, not because of the scenery, though Denmark does have a charming supply of windmills and bicycles, but because it's where some of the strangest ideas in physics were first seriously discussed, argued over, and quietly accepted. At the heart of this story is Niels Bohr, a Danish physicist with a gentle demeanor and a taste for long, complex sentences. Bohr helped shape one of the most influential views of quantum mechanics, a perspective that came to be known as the Copenhagen interpretation. The idea is deceptively simple. In fact, that's part of its charm. According to the Copenhagen view, quantum systems don't have definite properties until they're measured. An electron doesn't have a fixed position. A photon doesn't commit to a particular polarization. A particle doesn't choose a state until an observation forces it to. Before measurement, reality is a fuzzy cloud of possibilities. A probability wave measurement doesn't just reveal something that was already there. It creates the outcome. In other words, reality isn't quite real until we ask it to be. That's a bold statement, and it's the kind of thing that makes philosophers sit up and physicists reach for coffee. But Bohr and his colleagues weren't trying to make the universe mysterious for the sake of it. They were trying to make sense of experimental results. Every time they tried to treat particles like little billiard balls, the math fell apart. But when they treated particles as probability waves that only resolve upon measurement, things clicked into place. The wave function in this view isn't a physical thing. It doesn't describe a particle's actual position or momentum. Instead, it encodes everything we can know about the system. It's a mathematical catalog of possibilities, not a map of what is. This leads to one of the Copenhagen interpretation's central claims. Questions about a system's state before measurement are meaningless. Asking where the electron was before you measured it doesn't make sense because where only becomes a meaningful concept after the measurement. Reality is not something you peel back like a curtain. It's something that snaps into focus the moment you look. It's not that the particle was hiding its true nature. It simply didn't have one yet. Understandably, not everyone found this satisfying. Albert Einstein, for one, was famously uneasy with the idea. He wanted a universe that existed independently of whether anyone was observing it. He believed in an underlying reality, objective and deterministic, even if it was currently hidden from view. To Einstein, the Copenhagen interpretation sounded like saying, the moon doesn't exist unless you're looking at it. Bohr disagreed, but he didn't try to offer a grand metaphysical solution. Instead, he embraced a kind of pragmatic ambiguity. His position was that quantum theory tells us what we can say about nature, not necessarily what nature is. The role of science in this view isn't to discover what's really out there, but to describe the outcomes of experiments as precisely as possible. If that sounds a little unsatisfying, you're not alone. The Copenhagen interpretation is often accused of being more of a prescription than a description. It tells you how to use the equations. It tells you what the outcomes will be, but it doesn't tell you what's actually going on behind the scenes. This gave rise to the now infamous phrase, shut up and calculate. It's not a quote from Bohr himself, but it captures the mood of many working physicists. The idea is, stop worrying about the metaphysical implications and just use the theory. It works. It gives correct predictions. Isn't that enough? And to be fair, the Copenhagen approach does work. It's the default interpretation used in countless textbooks, labs, and classrooms. It underpins the design of semiconductors, lasers, and quantum computers. It has never failed an experimental test. For many scientists, that track record outweighs any philosophical discomfort, but still, the discomfort lingers. If reality only becomes real when measured, what does that say about the universe before observers existed? Did nothing have definite properties before conscious life arrived? Was the early universe in a kind of suspended animation waiting for someone to look? Most physicists would say no. The Copenhagen interpretation doesn't require a conscious observer, just an interaction with a measuring device or with the environment. Observation in this context is just a process of extracting information from a quantum system in a way that forces it to pick a side. But even this leads to more questions. What counts as a measurement? At what point does the wave function collapse? Why does the universe follow this strange rule at all? The Copenhagen camp tends to answer with a shrug and a smile. The theory doesn't explain why collapse happens, it just says when. If you want a deeper explanation, you'll need to look elsewhere, and many have competing interpretations like many. Worlds, pilot wave theory, and objective collapse models all aim to offer a more complete picture. Each tries to preserve some classical intuition, that reality exists independently, that cause leads to effect, that observation doesn't get special treatment. But each of these alternatives comes with its own complications. Copenhagen, by contrast, is lean. It doesn't introduce hidden variables. It doesn't multiply universes. It just lays out a set of rules. Calculate the wave function, apply the measurement, postulate and predict the outcome. Simple, direct, effective. Maybe that's its appeal. In a field full of strange possibilities, the Copenhagen interpretation offers a kind of calm. It's not trying to solve every mystery. It's content to describe the world we can see, measure, and interact with without claiming to know the deeper machinery behind the curtain. And maybe that's enough. Bohr often spoke in layered, almost poetic language. He once said, "Those who are not shocked when they first come across quantum theory cannot possibly have understood it." He understood that the Copenhagen approach wasn't about making peace with reality. It was about making peace with uncertainty. Quantum mechanics is weird, but rather than wrestle it into something tidy, the Copenhagen interpretation invites us to accept that weirdness and to work within it without demanding that the universe explain itself. It's not a final answer. It's a quiet rule book, a reminder that in the quantum world, simplicity and discomfort often travel together, and that sometimes the best we can do is shut up and calculate. The many worlds interpretation. Imagine you're holding a coin between your fingers. You flip it. It spins through the air, gleaming in the light, and lands with a soft clink. Heads. But according to one interpretation of quantum mechanics, something else happened too. Somewhere, not here, but still real, the same coin landed. Tails, and somewhere else again it landed on its edge, rolled off the table, and landed under the couch. Every possible outcome of that flip unfolded, not as a maybe, not as a probability, but as a real branch of reality, and you just happen to find yourself in the one that saw heads. This is the strange and elegant idea behind the many worlds interpretation of quantum physics. It began as a thought experiment, an alternative way of looking at the infamous wave function collapse problem. You may remember the wave function, the mathematical cloud of probabilities that defines everything about a quantum system. In the traditional Copenhagen view, when you make a measurement, the wave function collapses and one possibility becomes real. But what if it never collapses at all? In 1957, physicist Hugh Everett III proposed a radical idea. Maybe the wave function is always evolving smoothly and deterministically. Maybe when you measure a system, you don't force it to choose a single outcome. Instead, you split. The universe splits. Every possible outcome plays out, but each in its own separate branch of reality. It sounds dramatic, like something from science fiction, but Everett wasn't writing a novel. He was doing math, and his version of quantum mechanics is mathematically identical to the standard version, just without the extra rule that says collapse happens when you observe. In his view, the wave function never collapses, it only branches. Here's how it works. Imagine an electron with two possible spin states, up and down. If you measure its spin, classical quantum mechanics says the electron is in a superposition of both states until measured, at which point it chooses one. Everett says no choosing necessary. Instead, the measurement causes the system and the observer to split into two correlated branches. In one, you observe spin up. In the other, spin down. Both outcomes are real. Both versions of you exist, each in a different branch of the universe. No randomness, no collapse, just a growing, branching tree of reality. This may sound like a recipe for science fiction overload, parallel universes, doppelgangers, infinite copies of everything. But the many worlds interpretation doesn't rely on fantasy. It doesn't propose new physics or untested forces. In fact, its central appeal is that it sticks only to the mathematics we already use. It simply refuses to add the extra assumption that something magical happens when you look. To supporters of many worlds, this is its strength. The idea is weird, but the math is clean. Of course, not everyone is comfortable with this. For one thing, if the universe is constantly branching into new realities, where do all these universes go? Are they stacked on top of each other, floating in some higher dimensional multiverse? The theory doesn't say, and that's part of the philosophical tension. Many worlds isn't a theory about the structure of space. It's a statement about how quantum systems evolve. The other branches are real, but they don't interact with ours. Once a split occurs, the branches decohere, meaning they no longer interfere with each other. They become, for all practical purposes, invisible. That makes the theory hard to test directly. After all, if we can't observe the other branches, how do we know they're there? That's the central criticism. Many worlds may be elegant, but is it falsifiable? Can you prove it wrong? Supporters argue that's the wrong question. They say it's not about adding new predictions, it's about not adding unnecessary assumptions. If the wave function evolves smoothly according to the Schrödinger equation, and that equation never includes collapse, then why assume collapse exists at all? Occam's razor, often paraphrased as the simplest explanation, is usually the right one. Cuts both ways here. Copenhagen keeps the universe small by adding collapse. Many worlds keeps the math simple by accepting a very large universe. But is that universe too large? Let's take a calming moment to imagine the scale. Every time a quantum interaction has multiple possible outcomes, the universe branches. That includes not just lab experiments, but molecular collisions, radioactive decays, photon emissions, and everything else. The universe isn't splitting every now and then. It's branching constantly, exponentially, unimaginably. But in the same way, we don't feel the earth spinning under our feet. We don't feel the branching. To us, it's invisible, seamless. We simply see one outcome as if that's all there ever was. It's also important to say that in many worlds, these other realities aren't parallel lives in the sci-fi sense. You're not hopping between them. You don't get to meet your other selves. Each branch is causally isolated from the others. There's no communication across the divide. No peeking at other versions of yourself eating soup instead of salad. Once a split happens, it's permanent. This avoids a lot of the philosophical headaches that come with wave function collapse. There's no need to define what counts as a measurement, or when reality becomes real. Everything evolves smoothly. Measurement is just entanglement. You and the system become linked and the world unfolds accordingly. But that calm elegance also comes at a cost. If every possible outcome happens, then why do we feel like only one outcome occurred? Why does it feel like the coin landed heads and not tails? If all outcomes are real, what does probability even mean? Many worlds redefines probability not as the chance that something will happen, but as a measure of how much of you ends up in each branch. It's a subtle shift. Instead of asking what are the odds, you ask what fraction of my future selves see this result. It's not intuitive, but neither is quantum mechanics in general. And despite all its strangeness, many worlds has inspired deep, serious research. Some physicists believe it could help unify quantum mechanics with gravity. Others see it as a foundation for understanding quantum computing, where superpositions and entanglements do computational heavy lifting across possible. Imagine pulling back the curtain on everything. The stars, the oceans, your chair, your hand, even the light falling gently on your pillow. What if all of it, all matter and energy, wasn't made of solid things at all? What if the most fundamental stuff of reality wasn't stuff at all, but vibrations, waves, invisible ripples spreading through fields that fill all of space? Welcome to the quiet but profound world of quantum field theory, where the universe is not built out of particles, but out of fields that shimmer beneath everything. Let's start gently. In classical physics, a field is something that assigns a value to every point in space. A familiar example is the electric field, an invisible force that tells a charged particle how it should move. If you put a positive charge into an electric field, it feels a push. That's the field at work. Fields are smooth, continuous, and fill the universe like invisible jelly. Now, quantum mechanics comes along and sprinkles uncertainty onto the picture. It says fields don't just sit there quietly, they fluctuate, they buzz even in the absence of any real particles. Every field, electric, magnetic, gravitational, is quantum in nature. It jiggles even when it seems empty. Even the vacuum, as it turns out, isn't truly calm. It's restless. And here's the leap. In quantum field theory, or QFT, everything is a field. Every particle you've ever heard of, electrons, photons, quarks, neutrinos, is just a little blip in its corresponding field. A particle is not a tiny marble flying through space. It's a localized ripple, a bump, a wiggle in an underlying field that fills all of reality. Let's take the electron. Somewhere out there in space is the electron field, a quantum field that exists everywhere. When you see an electron, you're not looking at a separate self-contained object. You're observing a specific quantized excitation of that field. The field got excited in a localized way, and that's what you call an electron. Same goes for photons. The electromagnetic field fills all of space. When a light particle zips by, it's not a little bullet, it's a ripple, a tiny vibration in the electromagnetic field. Turn the knob on that ripple just right and you get visible light. Turn it differently and you get microwaves or X-rays. But it's all just modes of dancing in the same field. There's a field for every known particle. Quark fields, gluon fields, Higgs fields. Even the elusive graviton, if it exists, would be a ripple in the gravitational field. So where did our old friend the particle go? In a sense, particles are a useful fiction, a way to describe the behavior of fields in certain contexts. When the field is localized and the ripple behaves as a discrete packet of energy, it's convenient to call it a particle, but that's just our label for a behavior. The field is fundamental, the ripple is what we see, but the field is what's really there. This shift in perspective is profound. It turns the universe from a Lego set made of tiny blocks into something more like a symphony, an infinite orchestra of overlapping notes with reality emerging from their interference and harmony. Quantum field theory also explains some puzzling features of quantum mechanics that standard quantum theory struggles with. For instance, how do particles create and destroy themselves in high-energy reactions? Simple. They're just field excitations. Smash enough energy into a region of space, and you can jiggle a field hard enough to spawn a new ripple. That's how particle collisions in places like CERN can produce entirely new particles out of what seems like thin air. And what about antiparticles? The electron's shadowy twin, the positron. In quantum field theory, antiparticles are just another mode of excitation in the same field with opposite properties. Nothing spooky, just more symmetries in the rippling. Here's a particularly elegant twist. Forces themselves are mediated by fields. The electromagnetic force, it's the result of charged particles exchanging photons. Ripples in the electromagnetic field, the strong force. It's gluons vibrating in the gluon field, binding quarks together. Gravity, if it's ever successfully quantized, would involve tiny ripples in the gravitational field. Gravitons, even empty space isn't really empty. Quantum field theory predicts that fields are never completely still. They're always jittering with vacuum fluctuations. These fluctuations can have measurable effects like the Casimir effect, where two metal plates placed very close together in a vacuum feel a force pulling them together, caused by changes in the field's energy between them. There's something wonderfully serene about this picture. The idea that space itself is not a passive backdrop, but an active participant. Every point in space is alive with potential. Every particle, every interaction, every beam of light or burst of energy is just the field expressing itself. Of course, quantum field theory is complicated. It's not something you can casually calculate on a napkin, unless your napkin is the size of a blackboard and your chalk is labeled Feynman diagrams. But the conceptual takeaway is elegant. Nature at its most fundamental is not made of things. It's made of excitations, patterns, energy arranged in space and time. Even mass, the stubborn weighty quality of matter, is in many cases an emergent feature of field interactions. The Higgs field, discovered experimentally in 2012, is responsible for giving many particles their mass. Particles interact with this field like swimmers moving through molasses. The more resistance they feel, the more mass they appear to have. Here we are nestled in a world of fields. You, as you listen to this, are a delicate pattern in the electron field, the quark field, the photon field. Your thoughts are patterns of excitation. The very atoms of your body are nodes in a cosmic meshwork of fields humming in invisible harmony. You don't end at your skin. The fields that define you spill out into the universe. There is no sharp edge, no hard boundary, just softer or stronger ripples fading into the broader sea of quantum reality. Quantum field theory doesn't just describe the universe. It is the universe, or at least it's the best map we've drawn so far. A map where reality is not made of things bumping into each other, but of fields interwoven in a dance too fast, too subtle, and too beautiful to ever fully catch. And if you're still awake, you might be wondering, if everything is a ripple in a field, what are we rippling through? That, dear listener, is a question for another dream. The standard model if the universe came with a cookbook. The standard model of particle physics would be its ingredient list, minus a few mystery spices like dark matter and dark energy. It's a surprisingly compact recipe, elegant in its organization, and just a little bit chaotic in its naming conventions. But for all its quirks, this model is one of the most successful theories in the history of science. It tells us what the universe is made of, how those parts interact, and why reality looks and behaves the way it does. Let's start by introducing the cast. At its heart, the standard model is a collection of elementary particles. Particles that, as far as we can tell, cannot be broken down into anything smaller. You can think of them as the fundamental building blocks of matter and force woven together by the threads of quantum fields. There are three broad families: quarks, leptons, and bosons. Quarks are the stuff of protons and neutrons, the solids, core of atoms. There are 6 types or flavors of quarks: up, down, charm, strange, top, and bottom. Yes, those are their actual names. Physicists can do the most precise math imaginable, but naming things, that's where the chaos blooms. The up, and down quarks are the lightest and most common. A proton is made of 2 ups and 1 down. A neutron is made of 2 downs and 1 up. That means everything you see, touch, or are is mostly up and down quarks, plus electrons, which we'll meet in a moment. The other quarks, charm, strange, top, and bottom, are heavier, rarer, and mostly show up in high-energy environments like particle accelerators or cosmic rays. They're like the special guest stars of the particle world. Flashy, short-lived, but important in the grand scheme. Next, we have the leptons. This group includes the electron, which you've met many times before, buzzing around atoms, carrying electricity, and generally making life possible. Electrons also have cousins. There's the muon, which is like a heavy electron, and the tau, which is even heavier still. Like the exotic quarks, these heavier leptons don't last long in the wild, but they show up in high-energy reactions and leave distinct traces. Each of these charged leptons comes with a neutral partner, the neutrino. There are 3 of them, 1 for each flavor, and they're incredibly light, incredibly fast, and incredibly aloof. Neutrinos barely interact with matter at all. Billions pass through your body every second without leaving a trace. They're the introverts of the universe, always present, rarely noticed. So far we have 6 quarks and 6 leptons arranged in 3 neat generations. That's 12 matter particles total, all dancing on a stage set by quantum fields. But matter alone doesn't make a universe. We need forces, the rules that govern how these particles interact. That's where the bosons come in. Bosons are the force carriers. Each fundamental force has its own messenger particle, a kind of quantum handshake that tells other particles what to do. For the electromagnetic force, the carrier is the photon, the particle of light. It's massless. It moves at the speed of light, and it keeps electrons bound to atoms. Without photons, chemistry and breakfast wouldn't exist. The weak nuclear force, responsible for processes like radioactive decay, has 3 bosons, the W+, W, and Z bosons. Unlike the photon, these are heavy, so heavy in fact that they're only involved in interactions at very short ranges. They help turn neutrons into protons and vice versa, fueling the fusion that powers stars. Then there's the strong nuclear force, the glue that holds quarks together inside protons and neutrons and binds those protons and neutrons inside atomic nuclei. Its carrier particle is the gluon, a massless but energetic force bearer that comes in 8 varieties. Gluons are like a very excitable group of toddlers in a ball pit, constantly exchanging energy, never sitting still, and entirely responsible for why your atoms don't fall apart. Finally, there's the newcomer, the Higgs boson. This particle was confirmed experimentally in 2012 at CERN and earned a Nobel Prize. The following year, the Higgs boson is the manifestation of the Higgs field, which permeates space and gives mass to many of the other particles. Without the Higgs mechanism, the Standard Model would describe a very strange world, one where most particles zipped around massless, unable to clump together into atoms. So to recap, we have 12 matter particles, 6 quarks, and 6 leptons, and 5 force-carrying bosons, photon, WZ, gluon, and Higgs. All of this is the Standard Model, and it works beautifully. This model has predicted the outcomes of countless experiments with astonishing precision, from the behavior of particles in colliders to the decay rates of radioactive isotopes. The Standard Model just keeps being right. It's not perfect, but it's remarkably stubbornly good at what it does. Of course, it has a few holes. For one, it doesn't include gravity. The Standard Model is a quantum theory, while gravity is best described by Einstein's general relativity, a classical theory. Merging these two frameworks is one of the biggest unsolved problems in physics. Then there's dark matter. Astronomical observations suggest that most of the matter in the universe is invisible and doesn't interact with light. The Standard Model doesn't account for it. None of its particles can explain the gravitational effects we observe in galaxies. And let's not forget dark energy, the mysterious force driving the universe's accelerating expansion. That too is outside the Standard Model's jurisdiction. In fact, the Standard Model describes only about 5% of the universe. But what a 5% it is. Every atom, every interaction, every burst of light, every breath you take, it's all contained within this shimmering lattice of particles and forces. It's often said that the Standard Model is complete but unsatisfying. It's like finishing a puzzle only to realize the image on the box was just a small section of a much larger picture. But still, what's there is stunning. Elegant symmetries, intricate relationships, and mathematical structures that link particles in ways that hint at a deeper unity. Some theorists suspect that all of this quarks, leptons, bosons may someday be unified under a grand unified theory or even a theory of everything. These dreams may lie beyond the reach of current experiments, but they're guided by the same spirit that built the Standard Model, the belief that nature is knowable, that patterns lie beneath the chaos, and that even the wildest forces obey quiet laws. So the next time someone asks what the universe is made of, you can smile and say, mostly quarks, a few leptons, and a handful of bosons. And then for fun you can add, oh, and don't forget the Higgs field. Without it, none of this would have any weight. It's not the full story, but it's a pretty good opening chapter. At the intersection of dazzling complexity and mathematical perfection sits a theory that might just be the crown jewel of physics. Quantum electrodynamics, or QED for short. It's the framework that explains how light and matter interact, and it does so with such precision that even the pickiest decimal places stand in awe. At its core, QED describes the quantum dance between electrons and photons. Every flicker of light, every spark, every push and pull between charged particles, it's all a performance choreographed by the rules of QED, and somehow, despite involving an infinite number of possible interactions and mind-bending probabilities, the final answers it gives match experiments with ridiculous accuracy. We're talking about predictions confirmed to better than 1 part in a billion. That's like measuring the width of North America to within the thickness of a human hair. Being right, so how does QED manage this? Let's start with the problem it solves. In the early 20th century, physicists knew that electrons interacted with the electromagnetic field. When an electron accelerates, it emits light. When it absorbs light, it changes energy levels. But calculating the exact behavior of these interactions at the quantum level turned out to be a nightmare. The equations blew up. Infinities appeared where they shouldn't. You try to work out how an electron emits a photon, and the math would spit out nonsense like infinite energy, which is not helpful unless you're trying to cook the entire universe. A physicist with an impish grin and a love for bongo drums, Richard Feynman. Feynman, along with Julian Schwinger and Shinichiro Tomonaga, found a way to make QED behave. But Feynman went one step further. He made it visual. He invented Feynman diagrams, a graphical way to represent particle interactions that turned complicated quantum calculations into almost childlike scribbles. In these diagrams, particles are lines. Time flows from left to right. An electron might enter from one side, emit a photon, and then continue on its way. That photon might zip off and hit another electron, or loop back around and affect the same one. Each of these paths has a mathematical expression, and QED tells you to add them all up. Not just the most likely one, but every possible way the interaction could happen. That includes some pretty wild possibilities. An electron emits a photon which becomes an electron-positron pair, which then annihilates and becomes another photon, which is absorbed again. These are known as virtual particles. They exist only in the mathematical interludes between real measurable events, but they shape the outcome in very real ways. This is where QED becomes less like physics and more like poetry written in calculus. It doesn't just account for what does happen, it accounts for everything that could happen. Every zig, every zag, every loop and squiggle is part of the final answer. And somehow, when all of those possibilities are woven together, the result is a prediction so precise it could tell you how an electron would behave on the far side of the galaxy down to the tiniest decimal. One of the triumphs of QED is its explanation of the anomalous magnetic moment of the electron. The electron has a tiny magnetic field. Like a miniature bar magnet, classical physics predicts its strength, but quantum effects tweak it just a little. QED calculates this tweak and matches the experimental result to over 10 decimal places. It's not just good, it's stunning. The theory also elegantly explains phenomena like Compton scattering, where a photon bounces off an electron, Bremsstrahlung, where a particle emits radiation when slowing down, and pair production, where light can transform into matter and antimatter. All of these processes, which sound like sci-fi spells, fall naturally out of the QED framework. It's worth mentioning that QED doesn't stand alone. It's the quantum field theory that describes electromagnetism, but it's also the prototype for other quantum field theories. The strong force has its own version called quantum chromodynamics. The weak force is handled by electroweak theory, which unifies electromagnetism and the weak interaction. But QED came first, and it set the standard. And here's something charming. Despite its mind-melting math, QED is deeply intuitive once you get the hang of it. Feynman himself often said that the rules of quantum electrodynamics could be written on the back of a napkin. In his signature style, he boiled it down to this: particles take every possible path, each with a probability amplitude, U square. The sum to find the actual probability, and that's it. The rest is just bookkeeping. This idea that nature explores every path is at the heart of the quantum worldview. An electron doesn't just go from point A to point B. It takes every route through every obstacle around every tree and under every bridge all at once. The universe is calculating all of those possibilities, and QED is how we peek into that process. It's also a testament to how weird quantum physics can be without breaking down. You might think, surely a theory this strange must have limits. And you'd be right, QED doesn't include gravity, and it doesn't explain dark matter, but within its in his 1985 book, QED, The Strange Theory of Light and Matter, Richard Feynman writes, "I think I can safely say that nobody understands quantum mechanics." That's a powerful statement from a Nobel laureate who helped build the very framework of the theory. So where does that leave us? We've traveled from the quiet beginnings of blackbody radiation to the mind-bending realities of quantum tunneling and wave function collapse. We've met particles that are also waves and a vacuum that isn't empty. We've touched on a reality that seems to be in multiple states at once, and a universe so deeply interconnected that measuring one particle instantly affects another, even across vast distances. And we've seen a theory, QED, that predicts these behaviors with stunning accuracy. Perhaps in the end, that is the point. Quantum physics may not be something we can fully grasp with our everyday senses. It's not intuitive, it's not simple, and it doesn't always make sense according to our classical rules. But what it does brilliantly. It allows us to build technologies that seemed like science fiction just a few decades ago, to understand the fundamental building blocks of the universe, and to ask even deeper questions about the nature of reality. The journey through the quantum world is a journey into the unknown. It's a reminder that science isn't always about having all the answers, but about embracing the strangeness of the questions. The universe is more mysterious, more beautiful, and more wonderfully complex than we could have ever imagined. I hope you've enjoyed this journey. Thank you for listening.